Hello, my name is Ofir, and this is the presentation on our paper entitled Utilizing Uncertainty for Efficient Learning of Likely-Admissible Heuristics. It is well known that having access to a strong heuristic can greatly improve planning performance. Unfortunately, in many cases, in order to construct such a heuristic, you need to incorporate a lot of domain knowledge into the heuristic, and this can make it difficult to handcraft such strong heuristics. An alternative approach is to leverage machine learning to learn a strong heuristic from data. For example, suppose you have a set of 15 puzzle tasks with different start states, and for each such task, you have a plan that gets you from the start state to the goal state. Given such a set of plans, we can then take each plan and for each plan iterate over the states of the plan, and for each state extract a set of relevant features as well as the corresponding cost to goal. We can then use this data to train a supervised machine learning model, such as a neural network. During the training phase, the input to the model will be the feature vector, and the output or the target will be the corresponding cost to goal. Since these models have the ability to generalize to previously unseen data, after training, they can be used as the heuristic. In particular, for any state S, we simply need to extract the features, push them through the model, and then get the corresponding estimate of the cost to goal, which we will denote by y hat. One of the appealing things about the machine learning approach is that it does not require us to have access to any domain knowledge. All we need is a large data set of plans for training. Unfortunately, in more complex domains, it can be difficult to construct such a training data set. In order to overcome this, previous work has introduced the idea of bootstrap learning of heuristics. Under the bootstrap learning approach, planning and learning are interweaved, and so with this approach, we no longer need access to an upfront data set of plans for training. The basic premise of this approach is as follows. We start out with a weak heuristic H0. This can be a completely uninformative heuristic, such as a neural network with random weights. We then repeat the following. We generate a set of tasks, each task having a random start state. We try to solve each task with the current heuristic in some time limits. If we can't solve enough tasks, we increase the time limit, and we keep increasing the time limit until such time as enough tasks are solved. Once enough tasks are solved, we update our current heuristic and make it stronger by updating it and training it on the plans of the solved tasks, thus making it a stronger heuristic. The bootstrap learning approach is appealing because it does not require access to an upfront data set of plans for training. However, it has two major shortcomings. The first is that training under the approach is inefficient. This is because the procedure generates random training tasks, and in the beginning, when the heuristic is weak, it cannot solve these tasks in the given time limit. Therefore, much time is wasted trying to solve tasks that are not solvable with the current strength of the heuristic. The second shortcoming is that the procedure outputs a final heuristic that produces high suboptimality. This is because the heuristic is non-admissible, and so the plans that it generates are in general non-optimal. As a result, the heuristic is always trained on non-optimal plans, and this compounds errors with each iteration of the procedure. Our contribution is to address both of these challenges within the Bootstrap Learning framework. In particular, we will leverage a Bayesian framework to address these challenges. In standard supervised learning, we learn a function that takes in as input x and outputs a point estimate y hat. That is our prediction, and it should approximate the training data. With the Bayesian framework, the input x no longer maps to a point estimate, rather it maps to a full output distribution. The mean of the distribution under a normal assumption is y hat, But we now have these two additional uncertainty measures that capture the variance or our uncertainty around the mean. We will now explain what these uncertainties represent via an example. Consider the following plot where the red circles represent the training data, the blue line represents the fitted model, and the bars represent the magnitude of the uncertainty. The first thing that you may notice is that the bars are larger in regions where we are far away from the training data. This is because we have not observed such data during training, and so when we make predictions in these regions, we have higher uncertainty. Epistemic uncertainty captures our uncertainty because of this component. Epistemic uncertainty can be reduced by adding more training data that covers additional scenarios. The second thing that you may notice is that even in areas where we have observed training data, we still have these uncertainty bars. Aleatoric uncertainty captures this component of the uncertainty. Aleatoric uncertainty arises because of probabilistic variation in the data that cannot be explained away, even if we add more training data. In our work, we leverage these additional uncertainty measures to overcome the shortcomings of the original Bootstrap approach, as was previously discussed. In particular, in order to generate training tasks more efficiently, we develop a new algorithm that works on the premise of seeking states with high epistemic uncertainty. We illustrate this on the 15 puzzle domain. Our algorithm starts at the goal state and looks at all possible next states and evaluates the epistemic uncertainties of these states. In this case, both next possible states have low epistemic uncertainty, which I've indicated with the color blue. Therefore, our algorithm can just pick one of these at random. Let's suppose we go in the direction right. Then this is the resulting next state. As before, we evaluate all possible next states and get a measure of the epistemic uncertainty from our model. In this case, the down action leads to a high epistemic uncertainty state, as I've indicated with the color pink. Therefore, this is the direction that we will go in. Now that we have observed a state with high epistemic uncertainty, we stop execution of our generate task algorithm, and this is the task that we will use to plan on and learn from. The key idea behind our algorithm is that once we've learned from this task, we would have reduced the epistemic uncertainty of the model. Therefore, the next time that we call generate task, we will generate a different task to what has previously been observed during training. This approach is much more efficient than random task generation. Our second contribution is to reduce the suboptimality of the original Bootstrap procedure. Recall that in the standard supervised learning setting, the output of the model is a point estimate y hat. However, with our approach, the output is a full distribution. Therefore, we are no longer restricted to using y hat. Rather, we can use a point on the left tail of the distribution that is more conservative. By planning with this point, our heuristic is more likely to be admissible, and we are more likely to produce optimal plans. Therefore, by using this heuristic and learning from these plans that are more likely to be optimal, we mitigate the compounding error problem that exists with the original Bootstrap procedure. In totality, in our paper we introduce a new Bootstrap learning algorithm that takes into account the enhancements that we have discussed in this presentation. In particular, we generate tasks efficiently, thus improving training time, and we plan with a more conservative value, thus reducing suboptimality. To illustrate our algorithm empirically, we plot a graph of suboptimality as we plan with a more conservative heuristic for the 24 puzzle domain. As can be seen from the plot, by planning with a very conservative heuristic, we can achieve a very low suboptimality that is just below 3%. However, as it turns out, there is a price to pay for this lower suboptimality. When planning with a conservative heuristic that is at the tail point of the distribution, the heuristic can become uninformative, and this tends to cause planning time to increase. We discussed this trade-off more in our paper. Thank you for your attention, and at this point I would like to take any questions from the audience.